So organic chemistry is a lot about electrons, and even more so about moving those electrons, because if you can figure out where they exist and then how to move them, you can do pretty much everything. So a couple things to remember. Electrons are unstable. They do not want to be on their own, so we need to get them into someplace happy. And then one of those restrictions is they don't like confined spaces. So if we can put those electrons in a more unstable place or in a tiny space, they're higher energy and much more reactive. So we can then do all sorts of fun things with them. So when we go through and look at reactions, atoms will combine to make less reactive electrons. So we'll want to put those electrons into a lower energy state, which means they're more stable, less likely to react, everything's happy. So what things actually involve happiness? So when we're looking at resonance, we want to find the most stable structure, or the most stable way to arrange the electrons around a given set of atoms. When we look at mechanisms, we use it to find a new structure. So how can we change the arrangement of electrons around a group of separate molecules to make new molecules? So then what defines this happiness? So we want lots of space. I mean, that's pretty much everything, or even humans. So we want to put our electrons onto larger atoms, and we want to place them someplace that actually wants them. So we want to place them on an atom that has a higher electronegativity, okay, than where they started. So those are kind of the interplay that we're working with, is ultimately size and electronegativity. So those are the two big key words that we'll keep referring to. You'll keep hearing me ask about size and electronegativity. When it comes to second semester, what you'll end up hearing a lot is just resonance. And resonance is really just a code word for size and electronegativity, looking at that interplay. So before we move further, I want to make sure you understand what an electron density map is. So if we go through and look at this map, what does it mean? Okay, so we color code different things to mean stuff. So blue, in this case, means a decrease in temperature change, believe it or not. So if we look at our key, the blue means that the temperature actually decreased, in this case over the time between 1951 to 1980, actually June 2013 to the average of 1951-1980. And we can look at the super red section being an increase in temperature by 7.4 degrees. So this is just, global warming plug, I guess, here. If we take a look, we see that largely the entire planet has increased in temperature, and has increased in temperature in sections that we would really have hoped it to not increase, say like the Arctic. But we can use the same kind of idea when we're looking at electrons. So if we look at an electron density map, in this case for ethanol, what we're evaluating or looking at is where the electron density is located. In this case, that red section means a high area of electron density, and these blue sections mean low electron density. So understanding this does a couple things for us. Number one, it tells us where our electrons are, which means we now have an idea on where it would react. So in this molecule, we would probably think that high area of electron density is going to contribute to reactivity. It'll want to react with something with low electron density. Conversely, we could potentially look at the low electron density site being a possibility for high electrons coming in and interacting with it. So finding the balance of where the electrons exist within the molecule through an electron density map is really important. Except looking at electron density maps is really, really difficult. And if we asked you to draw electron density maps for every single molecule, you'd freak out. So what we've done instead is kind of move towards looking at structures and resonance structures and having you evaluate those instead. So before we even do that, we want to make sure that we understand everything about the arrows. So what you should remember from Gen Chem or from first semester is that we've got reaction arrows, both reaction and equilibrium. We're going to see a lot more equilibrium arrows in second semester organic. But then the important ones for this little mini lecture are in red. We're looking at our resonance arrows, the double-headed arrow that we would draw between structures, and then our curved arrows, either full-headed or half-headed. So we can move at most 2 electrons with any given arrow, and then that can propagate with more arrows, but a single arrow is at most going to do 2 electrons. And if we're really, really unlucky, we'll also look at radical reactions, and those would involve that half-headed or fishhook arrow, which is looking at the motion of 1 electron. So whenever you use your arrows, remember, we're looking at moving a pair of electrons for the most part. So, resonance, it's all about where is the electron. So if we attempted to draw an electron density map for benzene, we would probably say that we've got a lot of electron density in those double bonds, and we could highlight those as red. Everywhere else, we don't have that electron density, so we could probably put those in as blue, the extreme circumstance. Okay, so we could end up with something along these lines. Well, it turns out that if we actually look at the legitimate electron density map for benzene, it looks more like this. And the interesting part of that is that the red section is not just in those 3 bonds, or those 3 pi bonds. Sorry, it's actually spread all the way through the middle, and that everything on the outside is blue. So it's kind of an interesting distinction. That means our drawing isn't perfectly accurate. We want to take a look at this a little bit closer. So maybe what's happening is that those electrons aren't specifically located in those bonds. Well, if they aren't specifically in those bonds, we have to be able to show some way to move them somewhere else. Okay, so what we'll do is take a look at resonance. So when we're trying to draw a resonance structure, find a source of electrons. Okay, these can be lone pairs or pi bonds. They can be anything, any source, anywhere. So pick any source of electrons that is a lone pair or a pi bond and attempt to move those electrons. When we're moving them, we'll move them either from the atom, in the case of a lone pair, to a bond, or in the case of a pi bond, we'll go from the bond to an atom. Okay? So we'll go really simple and basic first. So I'm going to pick this lone pair. I'm going to move those electrons to that atom, that carbon atom. Okay, remember, electrons cannot travel very far because they're very, very unstable. So when we go through and draw this out, with that single electron push, I want to redraw everything else that I didn't actually change. So everything else needs to stay exactly the same. Okay, so we can draw on, I'm going to really regret having put on those hydrogens. So we're going to draw on all of those hydrogens. I didn't touch these pi bonds. We'll draw those. And I put a lone pair here on that carbon. I could now go through and put in charges. And we'll go through and highlight those with red. Okay, and we now have a resonance structure. This resonance structure is awful because we have these charges. So what we're going to want to do is try and find some way to continue to move these electrons. So from this new structure, so as bad as it is, it's not invalid. Okay, we still have, for the most part, we haven't exceeded octets. We have a very unhappy carbon being positive because it's now missing its octet. But it's not super, super horrible. But I'm now in an interesting new situation. I have electrons on an atom, so I can move those to a bond. So we've got all sorts of options. We can go backwards, but then that really just takes us backwards. So that's a pretty pointless arrow to do. So let's ignore that one. Let's actually take them towards the hydrogen bond. Okay? Because this is still a valid arrow pushing. We are still attempting to draw this. Whether or not it's right is irrelevant at this point. All we're trying to do is see what can happen. End up with this structure, right? So everything stays the same except I've put that pair of electrons into a bond with that hydrogen. I still have my positive charge. Okay? So now we want to go through and verify that our octets are satisfied. Well, we're in the same situation with all our carbons. In fact, with the carbons, we're in the same situation we were before, but our hydrogen's a little bit different. This hydrogen has exceeded its octet. Okay, that means something is wrong. So we go back to our previous step. Actually, before we do that, we'll look at this and say, okay, is there a pi bond that I can break? Okay, we can't touch sigma bonds, but is there a pi bond? Well, yeah, there is a pi bond. I could break and put that right back. Okay, so I would go back to my drawing because the one I've drawn here is wrong. Okay, this is really bad because I've exceeded the octet. Okay, so I will now take my green arrow and I'll go back to my original drawing and I will add it back in there. So we're going to take the electrons that we put into that pi bond and we're going to put them right back on the atom. So now that we've added that extra arrow, let's go back to our structure and see what happened. Okay, our end result. So we formed a pi bond, but then we broke it, so we don't have that pi bond anymore, and we put those electrons onto our carbon. Cool, so we've done everything that those arrows show. Did I draw a resonance structure? No, I drew the exact same thing. Okay, so don't be afraid to just draw arrows and see the result of what happens, and evaluate stabilities and possibilities. Is that allowed? That kind of deal. Okay, so in this case, that didn't work, so I won't be doing that arrow pushing. Which means, do I have any other options? Well, I could move those electrons to this bond. So we'll go through the exact same situation that we did before. And we're now in purple. So draw our resonance structure forwards. Put on all our hydrogens. Pardon the slowness in drawing this all out. Pi bond, we did not move any of the other pi bonds, and now again we want to evaluate our octets. What happened with our octet? Well, hopefully you notice that this carbon has exceeded its octet. Okay, so this structure is now bad because we've exceeded octet. So our rule, okay, if not, break a pi bond. Well, we've got two pi bonds to choose from. We can either use the pi bond that we just formed, or we could break the new one. So we could break a new one and put those electrons there. So what we'll do is go back to our previous structure, since we've now identified this pi bond, and add that extra arrow to our previous structure, and now go through and redraw it. I know, you should be irritated with resonance. Okay? You should be so irritated after drawing all these structures that you start to see how the electrons move without having to draw all of these structures. So we can add on all our hydrogens. Oh geez, lots of hydrogens. Okay, we formed a new pi bond here. We still have our positive charge, and we now have a lone pair on that carbon. Cool, so we now actually have a different resonance structure with the negative charge now somewhere else on the structure. We can go through and attempt to move this again. And what you may have noticed in this process is that I went from atom to bond, and then I went from bond to atom, and now what we're going to do is another attempt here. We're going to go from atom to bond again, but just like we did before, we're going to run into an issue. We can go bond to atom, and we can generate a new structure where we now have phone. Okay, so if we draw on our extra hydrogens all the way around, okay, bond, bond, get in our charges, there's our positive, there's our lone pair. What you might start to see is what we've done is ultimately actually started to move our electrons, instead of going from bond to atom, from bond to bond. Okay, so that is a shortcut. You just have to be very careful when you use shortcuts. So we can add that as a third possibility here on moving our electrons from bond to bond. Okay, so if we add that in, that's where we moved from really, actually here to here is a bond to bond move. And yeah, those two are a bond to bond move. If we continue to do this electron pushing, what you should see that we end up with at a very end result of all of this is we end up with our electrons around our ring like so. And if we compare that back to where we started, you'll notice what ended up happening was our bonds all just moved one atom over. So our electrons don't exist in any one of these positions. They exist equally at all positions. That means our aromatic ring can build charge at each and every single one of those carbons, okay, both positive and negative. So this does a lot of things for this structure. Number one, it makes it incredibly stable, which means that we would not expect it to react very readily. So if you think back to when you talked about alkenes, or think forward when you're thinking about alkenes in first semester, that this structure should not react the same as a standard carbon-carbon double bond because the electrons are pushed all over to the structure. Okay, so it's understanding something about how those electrons move and where they move to that is going to change its reactivity. If we were asked to just provide resonance structures for our initial starting structure, so if I asked, give me the resonance structures for this, okay, for that one compound, what we would probably expect you to do is just provide this one. And the question becomes is why? Well, if we go through and look at each of the intermediate staged resonance structures, you'll notice each of those has charge and a separation of charge. So those are now higher in energy because of the charge. We tend to not look at those as heavily. If I want to understand something about the reactivity of where I have electron density in that structure to do a reaction, I will absolutely look at those structures because that's where I have charge. Okay? So it's kind of a dynamic. You got to play back and forth with your resonance and kind of go towards, oh, this is just strictly draw a good resonance structure, or I want to understand something about the reaction. Draw the first bad resonance. Okay, it's got to be the first one. So that explains why the electron density in our electron map is now centered throughout the entire middle of the structure and not just at individual double bonds. Okay, so resonance can help explain that. If we look at this new structure, which we'll see in this semester or second semester, we can go through and again do resonance with this. Options to consider. We could try and bring the pi electron or the lone pair down, but we'll exceed the octet on the carbon, so we'd have to break a pi bond. We'd end up pushing them right back, no resonance structure. So the lone pairs are not valid to move. That means we could then move to our pi bonds and decide how to move those. Let's take a look at first our polar pi bond. We've got two options. We can move the electrons towards the oxygen, or we could move them towards the carbon. Okay, and we'll end up with slightly different results in both these circumstances. And while both arrows are valid, one is for sure better than the other. Okay, so let's take a look at those two structures and try and decide why might one be better than the other. And I'll add the lone pairs here. Get them in the right colors. So now that we're looking at our structures, which one of these is better than the other? Well, hopefully what you can see is that our red structure is by far better than our purple. Okay, and the reason being is that we've put the electron density, our charge, okay, our electrons, on an atom that would rather hold them. We're looking at a negative oxygen versus a negative carbon. Oxygen, being more electronegative than carbon, is going to prefer to hold those electrons. So while both of these are possible resonance structures and can exist or can contribute to it, the purple one has such a low contribution factor that it really just does not make sense to look at it. Remember when we said we want to look at the reactivity, we look at the first best or first worst resonance structure. That purple one is like second, third, fourth, fifth. I mean, it's pretty horrible as far as the resonance structure goes. So we effectively ignore it. So this first resonance structure tells us some chemistry. We now have an oxygen that's negatively charged, so it'll react with a positive. We also have a carbon that's positive that could react with a negative. But do we have more resonance? Well, I'm drawing the arrow, so of course we do. we can take the pi bond in that other alkene and shift those electrons up to make a pi bond internally. That then puts a positive charge at the very end. Why has this become important? Well, now I could have the negative attack that other carbon. So we have two sites of reactivity. The only way we really find these two sites, well, there's two ways. One, we do the reaction. Oh, yeah, it reacts at both sites. Okay, well, that's really easy for us to say in lecture, but then how are you going to test that? Well, we'd have very limited time, so you can't test it. So what you would need to do is be able to use resonance to predict that that is a possibility. And what we'll talk about later in the semester is what variances, what changes can we make ultimately actually to the negatives here as to where I would expect it to attack. Either the carbonyl carbon or the beta carbon. Okay, so that becomes a little bit trickier, and we really only know that through our resonance. So that's why you need to practice resonance. And when we look at our electron density map, you'll notice that we should see a lot of electron density up on our oxygen because both of our resonance structures showed that. You'll notice there's a little bit of green in here showing a little bit higher electron density, but you'll also notice that we really get some purples in here and kind of in the back of that one. And that's because there's very little electron density at those positions, which also suggests that this carbon and this carbon are not as positive, not as reactive, which is what our resonance structure showed. Okay? So it's trying to evaluate the interplay between all of these. When we look at a mechanism, it's pretty much the same rules, except in a mechanism we can break sigma bonds. So what we're going to end up doing is breaking the easiest bond first, which will be a pi bond, but then we can go back and break sigma bonds, which will be necessary if we're going to go through and make a reaction. So with this individual reaction here, we could go through and add curved arrows in to represent this. So we could say, well, the bromine needs to go here, and since the bromine will most likely be negative because it's more electronegative than the hydrogen, that means this pi bond has to shift here, which means these electrons have to shift out. Okay? These arrows are actually phenomenally good. What we've shown is how the electrons move, and we've shown them all in a valid way. We've tried to represent how everything is shifting and moving between this. But we do run into an issue with a mechanism. Our mechanism is supposed to represent the simplest step of a reaction. Okay? And if I add all of these arrows, however correct as they may be, all right before my reaction arrow, what I'm saying is that every single one of these things happens at the exact same instant. That is highly, highly unlikely. Okay, there's just too much going on there. So what our mechanism will do is take those arrows and break them up into smaller chunks that actually make sense. That making sense of those mechanistic steps becomes tricky and requires a little bit of practice and getting used to what things can happen and when they can happen. So if we go through and fix this up, we can end up with a variety of results. This ends up being a lot longer of a mechanism than I'd expected. So boo-hoo for me and excited for you. Can draw that arrow moving over. The relationship between these last two structures that I now have are resonance structures, which means if I'm looking at a mechanism, I need to make sure that I've got my resonance double-headed arrow here. If I want to further accent that, I can go through and put brackets around them. I still have that bromide floating around. That can now go in and attack that carbocation, and I can end up with my final product. Okay? So it's evaluating each and every single one of those steps. You're still looking at how the electrons move. We're always moving the electrons from a source to where they're lacking. Okay? Personally, I probably would have started with the HBr, because I know those electrons are going to go from the hydrogen to the bromine. Bromine's a good electron attacker, but there's no place for it to attack according to my product. That means I'll shift my focus to the positive hydrogen, and now what I want to do is find some place, the best source of electrons for that hydrogen, which according to my product, are probably going to be the oxygen. So I'll have the oxygen share the electrons across. So it's all a question of trying to pick up the balances between and what those intermediates are. And yes, that takes practice in lectures. Okay. So here's yet another practice. I'll give you a chance here to go ahead and pause, and then we'll put up the answers here in just a second. And here are our answers. With our first resonance structure, decided to show it in red. So the red curved arrow represents how we get to the red structure. The blue curved arrow represents how we got to the blue structure. Then added the purple. So if we added pretty much the opposite color arrow in, we would end up with our purple structure. And if you take a look at that final purple structure, hopefully what you represent, or what you can see, is a really bad combination, is we have two positive charges next to each other. What we'll see in second semester is that these drawings actually prove why this structure, this intermediate, is very, very unstable and very unlikely to form. Kind of an interesting result, which means we can actually predict that we would not generate a final product that came from this intermediate. Okay. The next one was a little bit trickier because I just gave you a formula, but you should be able to put that one together. It is not cyclical, so don't draw it as a circle. And we've got two resonance structures that can bounce back and forth on that. When we add our curved arrows, that first one is an oxidation reaction using chromic acid, and from that intermediate, given those products, we just have to kind of draw our arrows to make sure that we generate that result. One of the things that you've got to watch out for sometimes with mechanisms is maybe we'll give you a clue that the chromium took the electrons, maybe not. Okay, so you've got to kind of play around with what's there. The other clue that you've got is that you end up with a positive hydrogen. So that means the hydrogen back in our starting material had to have lost the electrons. Those electrons have to go somewhere. It does not make sense for them to jump up to the chromium because that is distance-wise too far away. It just doesn't make sense to do that. Okay? So it's a question of just trying to come up with the best possible way to represent that. Shorter distances are better. And then in that last one, we went through and gave you a bunch of arrows. Usually confuses the heck out of people, which is good. Now what you need to do is just kind of slowly process your way through and show how each of those bonds formed. Okay? Hopefully you're able to pick that one up without too much difficulty.